Thanks a lot for the invitation, and it's a pleasure to be here to speak about tropical geometry. It's a subject that I'm not really an expert in, but I would like to use it to study basically complex singularities, complex analytic singularities. Yeah, I'm going to start with just mentioning a couple of references and motivation. So Patrick Popescu-Pampu and Dimitri Stepanov published this article about local tropicalization, which caught my eye a few years ago, and I've been sort of using that article as my go-to reference to tropical geometry, and as well as, of course, other classical books and things. And also this book by Mikalkin and Rao, which is quite recent. In fact, it's actually not even published, I think, but it's available on Johannes Rao's webpage at least. And some of the stuff that I am doing in this talk is from that book, basically, or at least I wrote it one of those things. But the initial idea that sort of sparked this project of mine is a statement from an article by Wagreich from 1970, which expresses the multiplicity of a surface singularity in terms of an intersection number. So a very topological intersection number. And so let me mention just quickly in the beginning here the definition of the multiplicity. We're given a Noetherian local ring of dimension d, and the Hilbert Summer function is defined by just measuring the length of quotients of the powers of the maximal idea. So for me, this local ring will always be an analytic algebra, so just the local ring of a point in a complex analytic space. But, of course, you can replace that with an analytic variety or algebraic variety or whatever you want, probably. And so the Hilbert-Summer polynomial is a polynomial that takes the same values as the Hilbert-Summer functions for large k. And the leading coefficient of this polynomial essentially is the multiplicity, so normalized by this factorial d there. So for me, I'm just going to take an analytic space X with a point small x in it, and I'll just define E of this germ. That's just the multiplicity of this local. And by the way, if there's any questions, just let me know, because I see the same thing that you see. So if somebody puts something in the chat, I will see. So just say it. So Wagreich's theorem that I mentioned is the following. So we have a complex analytic surface singularity. So that just means we have a complex surface, so a two-dimensional analytic space. It can be an algebraic variety. And we choose a singular point. It doesn't have to be singular, but we choose a point on it. And we resolve the singularity. And one assumption that has to be made is that this factors through the blow-up. Basically, this means that the linear system, which you get by pulling back the maximal ideal, is has no base points. And so if you resolve a surface singularity, the pre-image of, so what you get is basically a smooth complex surface, so homomorphic manifold of dimension 2, and a bunch of curves on it, which is the pre-image of the origin. So that's the exceptional dimension. And the pullback of the maximal ideal is just, in this case, it's locally free sheaf, which is given by a cycle. And this cycle is denoted by the Z max, the maximal cycle. And so Wagreich's theorem, which can be proved in topological terms, using topological methods, is just that the multiplicity is minus this maximal cycle squared. And I kind of started studying local tropical geometry more carefully well, one motivation was to try to realize this theorem for Newton-degenerate surface singularities in C3, and have some kind of a formula in terms of the Newton diagram of a singularity for the multiplicity, which at the level, at the surface might seem a little bit stupid, because you can very easily compute the multiplicity of a hypersurface singularity from the Newton diagram of the function. But I wanted something that can be computed somehow by many terms, that each of them comes from something local. So I wrote down here a sketch of this proof, but I'm maybe going to not go through that. It's a topological sketch. So the proof is just you do a little bit of topology, and you have to use the fact that if you have a generic projection from your surface singularity to C2, then in a small neighborhood of the origin, the number of pre-images is there. So like if you take the pre-image of a point, then the number of points in that pre-image is the multiplicity. And here's a picture of this topological proof for the D4 singularity. So a resolution of the D4 singularity can be seen on this picture, where basically you have 4 curves. If you pretend that your computer monitor is a complex surface, and these black lines are the curves in the surface, and by taking the value so if you take 2 linear functions, h1, h2, and you count the points where h1 equals some small number, eta, and h2 equals 0, you see that you get projection points here between the 0 set of h2 and the pre-image of eta by h1, and the multiplicity is plus 2. And here you see the maximal cycle on this. So you have a resolution graph. I'm not going to go into definitions of that, but you work with those. And then basically this graph encodes the maximal cycle, and its square is -2. Essentially, you take this, you see this arrow here, and there's 1 on this arrow, and then you have 2 here, and the square of this becomes this times this, which is -2. That's the calculus of that. And but I'm going to be working inside what is referred to as linear varieties. And so we start with a standard toric setup, where basically n is a lattice, so an abelian group with a dual n, and we have a cone inside of Rn. And this is a finitely generated, let's say, rational, strictly convex cone of dimension r. So really, we want to have so our base space is essentially an affine toric variety with a fixed point, which is like the origin of that. If you don't want to use too much tropical toric stuff, then you can just say that this sigma is the positive orthant in Rn, or r to the power r, let's say. So r is the dimension of the space here. And the toric variety we are working with is c to the power r. So I'm not going to talk too much about the definition of this space, but basically let's have a look at an example. So projective tropical geometry, particularly you can see this in the book by Michalkin et al., as well as other sources, where to some extent they talk about intersection theory inside TP2, where T is the tropical numbers. Local tropical geometry deals with essentially a neighborhood arrow at the vertex. And, of course, this could be higher dimensional if you will. And so the space where all the geometry that we're going to talk about takes place in is essentially this blue space. So in this case, this would be if the cone would be the positive quadrant in R2. And we have this linear variety, which essentially keeps track of all the strata at infinity. So for each phase of sigma, so if you have a phase tau1 like this, take the quotient by of the ambient n, so the real space generated by the real vector space generated, and you take the vector space generated by tau1 here, and you get this stratum at infinity. And similarly for every single phase. So if you, for example, divide out by sigma, you get this point here. And I should say I use this notation where you take the image of big sigma in this stratum is denoted by big sigma with this cone inside of parentheses. So yeah, and please stop me or ask questions if this is going quickly. But so I don't know if this is something that is completely trivial for a tropical seminar. This is something that everybody knows exactly what it is or not. But what we are going to be concerned with are cycles. So cycles are just going to be balanced weighted fans. So actually, these are all the polyhedrons that appear are cones. So which kind of refers to the fact that we're working on complex numbers instead of non-trivial non-Archimedean ring. So a weighted fan is just a formal sum of cones. So, and I'm going to stick to just cycles of pure dimension, but you can mix the dimension if you want. So a weighted fan is just a formal sum of cones inside of this sigma. One thing about this notation, which is, as far as I know, at least, is at least used in the article by Professor Campo and Stefanov, is that if we go back here to this example, this space here is denoted by this closure and also the open circle. So it's a sort of things. This just means that we take a closure within this projective space. So this means that we get all the strata at infinity. But this circle that says that it should be open means that this is an open subset of TP2. So this we forget about this this boundary of the cone here. So that's what I mean by this circle. And if you have a circle and you don't have the line here, then you don't have the strata at infinity, and also you don't have this boundary. So if we say that a weighted fan in this this open cone is just a formal sum of cones, and all of these summands are contained in sigma, and they are not contained in boundary. That's what the circle means. And we say that two such weighted fans are equivalent if you can get one from the other using subdivision, essentially. And for the most part, we will just assume that all weighted fans are regular. So it means that all the summands are regular cones. And we can assume that these cones generate a fan in some nice way, saying that the intersection of two cones is phase of either of them, and so on. And but we're going to define special weighted fans by the balance condition. So I will just spell that out here, which is basically something that is probably known for the geometers. So let theta be a a cone inside of sigma, which has one lower dimension than our cycle, and we choose all the summands in this weighted fan which contain theta as a face. And by the regularity assumption, we can assume that each eta I is generated by theta and one primitive vector as a cone. And the balanced condition is says that for every such theta, so not for the ones that are in boundary, but every theta in sigma, when you take this weighted sum of these vectors pointing away from theta, you get the sum of these vectors belongs to the group generated by theta. And it may or may not be inside of the cone theta, but it's at least in this group. And in this case, we say that the equivalent class of this weighted fan is B cycle in the open sigma. And we are going to be concerned mostly with a group of cycles which live inside of the closure of the sigma, as well as all the strata at infinity that come with sigma. And so we just take the direct sum for each of these cones. And so let me just to spell this out, in this example, you would have all the one-dimensional cycles in this picture would just be any formal sum of rays inside of this quadrant, and then you have one ray here on this infinitum, this stratum here, and one ray here. So you have two more, and then you don't have any one-dimensional cycles here because this one does not have a high enough dimension for that. And but so we define the group of cycles of dimension d as just set d of this closure of the open cone as just the direct sum. And if we have a cycle, if we take one of these cycles, we can take the set of cycles on that cycle and think of that cycle as a subspace. So usually I say that, okay, let's take an effective cycle. Effective just means that all the coefficients are non-negative, which may or may not be important for applications. So, and the support here just means, this means the, so I take the closure of the support. So that just means that you take the closure of all the cones that appear in the sum in this, in sigma bar circle. So for example, the support of a ray in this quadrant would be the ray going all the way to infinity, and also this point here at infinity. This would be the closed support. And this means that the cycles, even if this, even if you take T as just the cone sigma, then you would still get cycles that are supported at infinity in this group. Okay. So just some special examples. The set of zero-dimensional cycles is just a free abelian group of rank 1. It's generated by the point at infinity. So when you divide out by everything, you get a zero-dimensional space which consists of one point. And because we're only dealing with cones and not general polygonal complexes, this is the only point that we get. And actually a similar thing with the top dimensional cycles. There's only one essentially top dimensional cycle. It's the cone itself. Because if it's balanced, then you cannot start mixing different top dimensional cones. You're going to trouble. is a balanced condition. So we're going to identify this group, this set 0, with the integers. So what we're going to do in the end is we're going to take intersections which end up in zero-dimensional cycle group and say that these are basically numbers, taking a degree. So the main construction is the fact that for some germ, so actually, so maybe I forgot to write down this definition at some point in the beginning. So let U be the affine toric variety associated with the cone sigma, and then of course U is stratified into toric, and this stratification corresponds to the stratification of the closure of the cone sigma inside of this projective space. And the way that Popescu-Campo and Stepanov construct their tropicalization is by starting with the initial object being the semi-group morphism from the set of monomials into the ring. So this local ring of the germ Y is just the local ring of the space U divided by some ideal. So each monomial on U gives you a function on Y. And you get a semi-group morphism which produces for you a set in sigma, which is called trop bigger than 0 of gamma. And they prove that this is actually a polyhedral complex, or it is a union of a bunch of cones. And if this Y has pure dimension D, then these cones, all of these cones have dimension D. And although this is not mentioned in their article, you can give weights to these cones. So you can say that, of course, there's no canonical way of saying that this is a union of cones, but it is a union of cones in some way. And you can give weights to each of these cones in such a way that they are actually a cycle. This is a balanced weighted fan. And I'm not going to go into the details of that, but it's basically the same way you would for a variety in torus. And what you get is a cycle, a d-dimensional cycle for each subspace Y in the cycle group. So what you get is this object here, which is the central object of the story, a tropical cycle of dimension D, which gives you somehow a shadow of the tropical variety Y. And it is additive in some sense, in that you can think of this as like a tropical version of the cycle group, where basically you take ZD to be the group of cycles in the local ring of U. So it is freely generated by prime ideals of dimension D. And every freely generated module over the local ring gives you a cycle. And in particular, any subspace, you take the quotient of an ideal, which is a module, and it gives you a cycle. And this map factors through this universal map from the category of finely generated modules of the dimension at most D into the cycle group, the local ring. This is not going to be extremely important, but I think it's a nice thing to keep in mind as an analogy. And okay. So Cartier divisors have already been considered by some tropical geometers, certainly in the book by Lucas and others. And of course, in the case of you can take a piecewise linear function. You can think of a tropicalization of a polynomial as a piecewise linear function, and this is done in classical textbooks to get a tropical variety. And we are going to do the same thing in this, but we have to do this also with the strata at infinity. And the construction is very similar to the construction in the classical case for cycles in Rn. So we use the notation that I set up for the balanced condition. So well, we start with a definition of an object. So psi is a piecewise linear function from the support of T to R, where T is a d-dimensional cycle in the cone sigma. And let's take a cycle in the cone sigma to start with, rather than which doesn't have anything happening at the strata at infinity. So a piecewise linear function just means that this cycle is represented by a weighted fan in such a way that for every cone in this fan, psi restricted to this cone is a linear function. So there exists a psi eta for every eta, so that there's a linear function. So a linear function on eta and eta to R, so that psi restricted to eta is just this linear function. And of course, these have to glue together along faces, common faces of different cones. So this is a continuous function. And a Cartier divisor on a tropical cycle where you allow cones to appear on the strata at infinity is just a formal sum of such Cartier divisors for the different components. And we define so one thing or two things to keep in mind here, that this compatibility condition. So if theta is the intersection of two cones, then we want the restriction of these linear functions to agree along theta. But we only require this for cones that are not subsets of the boundary. So we allow, so if two cones eta 1 and eta 2 intersect in a theta which lies on the boundary of sigma, then these linear functions may actually not agree along theta. This is because, so this is something that would be happening far away from this point. And what we really want to work with is local tropical geometry. So we are looking at this space, space as like a small neighborhood around this point here. So we are actually thinking of local tropical geometry as working with the germ of a tropical space. And so something that happens along the boundary of this cone, it doesn't matter for us. Yeah, and another thing is that these functions for different tau's, so the functions that are defined along strata infinity will have to be compatible. That's not really so important. But it may be important for some applications. So the main thing here is that when you are given a Cartier divisor, you get a Weil divisor. And this is done exactly in the same way as in the classical case, at least to begin with, which is to say that you use the balanced condition. So let's assume that this, so we assume that this cycle T is represented by a weighted fan fancy T, and it's given by a sum of etas with some coefficients. and let's assume that all the etas are regular cones. And take a theta, which is a cone in one of the stratum, and theta is d minus 1 dimension. So we start by choosing all the cones eta 1 to eta s of dimension d plus of dimension d that appear in T, like we did in the definition of the balance condition. And vectors v1 to vs, which generate eta along with theta. And so these are the etas, actually, I should have written here, those which belong to the same stratum as theta. So theta lies in stratum given by tau, and these etas here, they should lie in the same stratum. And so by the balance condition, we have this v0, which lies in n theta. But we could have more cones that have theta somehow as their face. So if eta s plus 1 up to eta s plus t is these are all the cones that intersect, so that lie in higher dimensional strata and intersect this stratum sigma tau in theta. And we just take all such cones. And then the way that this works is that we have a canonical projection from the space n eta I to n theta. So let's just look at this picture again, because I like to use this picture. So this blue cone here is in some sense a face of this turquoise cone here. So this the big sigma is of dimension 2, and that could be one of their eta, and the blue one could be a theta, and it's not a face of this polygon in the classical sense, but of course on this picture you see that this is a face of this square, and you have a canonical projection, which is basically the quotient, where you quotient out by the group generated by tau 1 from this turquoise square onto the blue line there. And moreover, because the difference of dimension is 1, the kernel of this projection has dimension 1. And so this kernel is generated by an element that we just choose vi, and we choose it in such a way that minus vi is in the sigma, is in the cone. And we get a number. So with all this construction, we get a number, which is basically you apply the function phi theta to v0, which is possible exactly because of the balance condition. So v0 is in n theta. And then you subtract the sum of psi applied to all the other vectors. So vi for I going from 1 to s plus t. So this is somehow two sums. So like the first sum goes from 1 to s, and the sum from s plus 1 to t. And if t is equal to 0, then this is exactly the same definition as in the classical case, when there is no strata of different dimensions. So this is the classical definition of the cycle, which is given by a piece of linear function. So given by the tropicalization of some polynomial, for example. And so what we get is a definition here. We just put a parenthesis on this psi, and we sum up for every theta the cone theta with coefficient given by that sum over there. And this is so if t has dimension e, then this sum has dimension d minus 1 by construction. And one goes through the exercise of proving that all of this is independent of the representative fancy t, and so on. And we write this also sometimes. So if psi is defined on a bigger set than T, if you take, if psi is defined on T and you have a cycle S in the cycle group of T, meaning just a cycle that is supported on the same set, or like the smaller set than T, then you can take this kind of, you can use this notation here and think of it as a product, which is a little bit artificial maybe, but basically you just restrict psi to this subspace and you get a divisor, a cycle, which is has dimension 1 less than the cycle S. If you assume that S has positive dimension, S has 0 dimension, this is just 0. And so this is somehow an artificial way of obtaining some intersection theory in local tropical geometry. But if you want to have some actual intersection theory, then you would want this map to be injective, or at least this thing should only depend on the cycle. So if you take the cycle defined by psi, you would like to take the product with that cycle. So you would like to take a product with a Weil divisor rather than a Cartier divisor. And this is possible if this map is injective. And for example, in the case when this cone is, when the space that you are working with is the full cone. So if psi is defined on the whole cone rather than just some cycles in such space. But in general, it's not injective, I don't think. But this is a question that I've been looking at for as well. What kind of injectivity properties can be found for this kind of instructions in developing tropical geometry? But this is not something that is too important at this point, at least for the sections of the theorem that I want to get to. So tropicalizations of power series, this is of course the factory that gives you a lot of piecewise linear functions. This is why we call it, or this is why a Cartier divisor is a piecewise linear function, because it's a actual function. So a simple example here, if you take the cycle given just by some sigma, there should be a bracket around this thing, so that this is a cycle. I don't know. If you just take a function given by a linear function, so if u is in the dual space, so that's a linear function on sigma. In particular, it's piecewise linear. Of course, if you think of a linear function on just the space n, or nr, the divisor that it defines is nothing, so just 0. But of course, it defines a divisor that is supported at the step at infinity. In the same way that a monomial defines a divisor in a toric variety, which is invariant. So. And this formula comes out of this construction very quickly, that the divisor associated with the function psi equals u is just the sum of the component that start at infinity of codimension 1. And that's it. More generally, if you have a power series, then you can take the minimum of all these functions. So this symbol here I just used to say that you take the minimum of all these numbers coming from here, or you take the minimum of these functions. And this is the tropicalization of a function, basically in the classical sense. And so what you get is a Cartier divisor on the cone sigma from a power series. And the underlying set of the cycle that this Cartier divisor defines is in fact the tropicalization of the hypersurface. So if x is the hypersurface defined by the function f, and you tropicalize the hypersurface x, you get exactly the union of all the cones appearing in this Weil divisor associated with this Cartier divisor. And more generally, so this intersection theory doesn't run through completely. Of course, much like stable intersection theory, you have to take something generic, and it is enough for us to, if you say that, so let's take a subvariety or an analytic germ y at the origin of our toric space U, and take a non-empty set of the semigroup. So just a non-empty set of monomials that define regular functions in toric space, and you just take a somehow generic sum of these monomials. So this is just a function. So if this set is finite, then you get a polynomial. If it's infinite, then you may have to worry about convergence or whatever. But it's enough that these coefficients are generic in some nice sense, which is typically not so difficult to work with. And so we define a tropical cycle just by this function. So this is a cycle of codimension 1 in the space associated with sigma U. And now let's take the hypersurface inside Y, which is defined by F. So we restrict F to the space Y, and this gives you a hypersurface inside of Y. And we make the assumption that the function psi F restricts to this thing nicely. So this means that the function psi F does not take infinite values in a cone appearing in this tropical cycle. It can happen that this psi F takes value infinity at some strata at infinity, and that means that we are not allowed to have any summands in this weighted fan on that stratum. So basically, this translates to saying that the function f does not vanish completely on any component of y, which makes sense if you want to do intersection. So there's a lemma, which is that you take this this intersection here, which I defined because of the injectivity of the bio-divisor construction, and so the tropical cycle associated with X is just the tropical cycle associated with Y intersected with this TF, which is a very somehow logical result. And in particular, you can take a generic hyperplane section. So I'm going to define this T max on the next slide. If X is a generic hyperplane section inside of Y, then you can compute the tropicalization of X by just intersecting with T max, where T max is what perhaps everybody would expect it to be, which is you take a generating set of the semigroup of monomials. So if the semigroup, so if the toric space that we're working with is just C to the power R, then these are just the generators of the monomials, the x1 up to xr. But basically, a generic sum of these monomials will be a generic hyperplane section. And we define the psi max, so the Cartier divisor, as just the minimum of all these functions. So this is the tropicalization of the generic linear function. And we define the T max, the maximal tropical cycle, as just the associated bio-divisor. And a theorem, which is the main theorem of this talk, is we want to compute the multiplicity of the germ Y. And what we have to do this is essentially just take T max to the power B and intersect with T of Y. So basically, an analogous way to say this would be to say that the multiplicity is computed by taking a default hyperplane intersection, which actually doesn't work in algebraic geometry, because I mean this works if you have a Cohen-Macaulay ring. Then computing the multiplicity, in order to do that, all you have to do is take d generic hyperplanes and intersect them, and what you get is a ring of dimension 0, and so has finite length. In that length is the multiplicity. If it's not Cohen-Macaulay, then that does not work. That's not true. But luckily enough, in tropical geometry, it's true. So you can think of this as restricting the function psi max to the cycle. This t should be this t of y. So this big T here should be this cycle here associated with y. And you think of this as a piecewise linear function on the cycle, and you take its default product, and you get a zero-dimensional cycle. And the coefficient in front of the point at infinity is the multiplicity. And the way to prove this is actually not very difficult. So we do induction by dimension d, which is exactly the kind of argument that you would use for Cohen-Macaulay modules, but we are going to disregard. So you can use this kind of methodology if you are allowed to disregard at some point the components that appear along the way and do induction. So basically, because this is very additive, so this is like an intersection product, so everything is very additive, we can assume that y is an irreducible germ of pure dimension d. So if it does not have pure dimension d, we can throw away the embedded components or any lower dimensional components, simply because this does not change the multiplicity. So by construction of the multiplicity, so we don't worry about that. And so what we get is we have a tropical cycle Ty in Zd of the sigma. There should be a bar over the sigma here, because this could have. No, I'm wrong. There shouldn't be a bar there, because we can assume that because it's irreducible, we can actually assume that this tropical cycle doesn't have any components appearing at the start at infinity. So the induction starts at d equals 1. In that case, of course, it's the case d equals 0 is trivial. The d1 case, by our assumption, we can assume that y is a reduced curve in this toric space. And we can assume that the tropicalization of this curve is just one ray, and this ray has a multiplicity m. So where v is a vector, and we say that v, let's say, is a primitive element of the cone. We can assume that v is not on the boundary of sigma, and m is some integer. So we can resolve the curve by normalization, and we get this order function on a function ring. So we verify that for a monomial, the order, if you pull back by the normalization map, you pull back a monomial, and you evaluate that function. So you take the order of this. What you get is just the intersection of the exponent of a monomial with this m times v vector that is essentially tells you everything about the tropicalization of your space. And the multiplicity of an irreducible curve singularity is the smallest non-zero order of an analytic function. And so what we end up with very fast is that the multiplicity equals this minimum. So where you evaluate, or where you take intersection with all the non-zero monomials. So you just look at all non-zero monomials, you look at the order that appears, you take the smallest of these. And this is actually the smallest order that can appear in the semigroup associated with this branch. And basically by definition or by construction, if you look at the sequence of definitions, this minimum is precisely the maximal psi applied to this vector mv. And by further definition, this here is the intersection of this T max with this tropicalization, this tropical cycle. Now, if D is, so that proves the theorem in the case when Y is a curved term. And for higher dimension, you just take a generic hyperplane section and use induction. And we have to use this lemma here, which I said, the tropicalization of a generic hyperplane section is just T max times the tropicalization of Y. So you can use this theorem and you immediately get the result for this theorem, saying that you add one more product of this maximal cycle to your tropical product. And so on the picture in the beginning, I showed so there is this topological way of computing the multiplicity as a product, and along the way in that proof, you will take like a Miller fiber like this of a generic linear function, and then a strict transform of a generic linear hyperplane. So basically, that means you say one generic linear function equals some small constant, and the other generic linear function equals 0. This defines for you two curves, and these curves intersect exactly in E points, where E is the multiplicity of your singularity. And in the case of the before singularity, a generic linear function vanishes of order 2 along this curve here. And the strict transform of a generic linear hyperplane passes transversally once through that same curve. And so the number of points is 2. So that's the topological way of thinking about Wagreich's theorem, which gives you the multiplicity in terms of some intersection number. The way that you should think about the intersection that gives you the multiplicity in terms of local tropical geometry. So if you take a different look at D4, Mutsuo Oka wrote an article in the 80s where he gives a very explicit way of resolving Newton longitudinal singularities. In particular, this works for the D4 singularity. So this is a weighted homogeneous singularity with weights 2, 2, 3 on the variables x, y, and z. And so the tropicalization of this singularity will be you take the Newton diagram and or the Newton polyhedron, and you look at the dual fan associated with that polyhedron. And what you get is one special ray in the middle. So this green set is the. So I'm looking at this as, so this is something that lives inside of the positive octant in 3-dimensional space. And what this triangle here is just the convex, so the simplex, 2 simplex inside R3. So the vertices are really the natural basis vector of the real vector space. And you intersect the tropicalization, and you get something 1-dimensional. And these green lines are the intersection with this simplex of the tropicalization of the D4 singularity. And so this picture should be viewed as this one here, where I drew a picture of this in the computer, where you have some cones. And of course, these cones should extend to infinity. Here are the hyperplanes, which are not part of the tropicalization. And then you have one ray in the center, which goes to infinity. and here is the vector 2, 2, 3, and then you have 3 cones that somehow join this ray with something on the boundary. So this is the tropicalization. And if you cut this with a hyperplane that passes through this point and this point and this point here, then you get a triangle, and inside the triangle you get a point in the center with 3 lines. And if you do the same thing for the generic linear function, which is just x plus y plus z, you get a similar picture, but a simpler one. All the weights, so the red lines here represent the tropicalization of the generic hyperplane or generic linear function. And all these cones have weight 1, and here you have 2 cones with weight 1 and 1 cone with weight 2. And if you do, it's enough just to take the standard stable intersection of these 2 sets at this cone. So at this ray generated by this point here, which this is the ray generated by 2, 2, 3. And you see that T max times TF, where F is this function, is just that ray. And if you intersect this again with T max, you get 2, because the function T max is the minimum of these coordinates. And the minimum of 2, 2, 3 is 2. So psi max of this generator equals 2. And so what you get is the multiplicity of D4 is 2, which we knew already. But this is a way to see that formula. I don't remember. Yeah, this is the final slide. I forgot to put the obligatory thank you on the last slide, so I'll just say thank you so much for listening.